Today we're going to be talking about graphing rational functions. Uh, we will be able to use transformations to graph rational functions. We're going to be focusing more on the features of the graph than how to actually plot the points for the graph. We're going to get most of our points from Desmos. So, some new vocabulary. What is an asymptote? This is an invisible line that the graph never touches or crosses. So we won't actually see it when we're graphing in Desmos, but we'll kind of be able to tell where it is based on what the graph is doing. So the first form we're going to look at is kind of the general form that uses A, H, and K. We've seen lots of things with A, H, and K this year. And they're still going to adjust our graph as they have with all of our other parent functions. So like A is going to stretch or flip, H is going to move it left and right, and K is going to move it up and down. So if we look at our parent graph, which would be y equals 1 over x, our vertical asymptotes are going to come from our denominators. So since there's nothing in the denominator, our vertical asymptote would just be at x equals 0. Or horizontal asymptote is going to come from k. Since we don't have anything on the end here, it will be y equals 0. For domain and range, we started off the year writing in interval notation. You've also seen a little bit of set notation earlier in this unit. So for the domain, we could either write it as x such that x cannot equal 0. That's what you've been seeing me write when we were writing the domain, when we were simplifying and solving. You also could technically write it as negative infinity to 0 and 0 to infinity. I don't have a preference of which one you use as long as you're using it correctly. And you need to be able to recognize the two, like on a quiz, knowing that these are the same thing and understanding what they both mean. For the range, since we have an asymptote at 0, we can't touch 0 for this one either. The set notation would look just almost identical as the domain. We would just use y's instead of x's because now it's range. And again, you can write it in set notation. And just with the set notation, it's saying we're getting as close to 0 as possible, but we're not going to touch it. And then we're going to hop over to the other side, start really close to 0, and then keep on going away from it forever. So if we wanted to graph this, so put that dot there. So a vertical asymptote at 0. When we're drawing these on graph paper, we use dotted lines for the asymptotes to signify that we know they're there, but we can't touch them and they're going to be invisible. And if we plug in 1 over 1, plugging in 1 for x, we would get 1. 1 over 2 would be 1/2, and so on, getting closer. It's going to look something like that. And then in this corner, something like that. And don't worry about too much about how I got the picture. We're going to do more with Desmos in a minute. So end behavior as x goes to positive infinity. So this is going to be the first time that f of x is doing something. Actually, hold on just a second. So I'm actually going to write the end behavior off to the side just to make it a little bit easier to read. Alright. I'm going to put this over here. So as x goes to positive infinity, f of x is going towards. So as x goes to positive infinity, as the x's get bigger and bigger, this is going out to the side. It's sort of flattening it out, and it's getting closer and closer to 0. Then as x goes to negative infinity, f of x goes towards. So as our x's get more and more negative, again, this looks like it's flattening out, and it's getting closer and closer to 0. It's going towards that horizontal asymptote. Alright, so this time we have some h and k values filled in. So here, a is still 1, h would be 2, and k would be 1. So that means our vertical asymptote would be at x equals 2. So that's where our dotted line is going to be. Our horizontal asymptote would be at y equals 1. So like that. Now I could calculate and plug numbers in to figure out where it go and use transformations, but we're going to focus on using Desmos this time. So I'm going to go over to Desmos. Y equals 1 over x minus 2 plus 1. And you could try and get points off of here, like it gives us 1, 0 as an x-intercept, 0, 0.5. If you click the gear up here, you can change your equation into a table, and that'll sort of give us some points to put in. So 0, 0.5, that's there. So 1, 0. But we need something based on our parent graph. We know that there's going to be 2 quadrants with graph in them. So that helps us get what's going to be down in this corner. So we need something for the opposite corner. So it tells us 2 is undefined. That is a hint that that's where your vertical asymptote is. But if I start pushing enter here, it will give me some values on this side of my curve. So 3, 2, and 4, 1.5. 1, 2, 3, 1, 2, and 4, 1.5. And then use my curve to connect my dots and avoid touching the asymptotes. So our domain, we can either say x such that x cannot equal 2, because that's where our asymptote is, we're not going to touch it, or negative infinity to 2, union to infinity. And for our range, y such that y cannot equal 1, because that's where our horizontal asymptote is, or we can say negative infinity to 1, union 1 to infinity. Our end behavior, as x goes to positive infinity, f of x goes towards 1. This time, as they're getting bigger and bigger, it's getting closer to this asymptote, which is at 1. So basically, your end behavior is always going towards your horizontal asymptote. Now, this is in general form, transformation form, I don't know what else you want to call it. We've got a fraction, and then there's a thing on the end. But we also see rational expressions, and you've seen this more when we were simplifying and solving, that it's written as a single term. It's all in one fraction. So to find the vertical asymptote or asymptotes, there could be more than one. You're going to factor the denominators. And determine what will make those factors equal 0. Which is the same thing you've been doing when we write the domain in the simplifying, multiplying, adding, solving, all those problems when we were writing the domain. You're basically saying that's where the asymptotes are because x can't be those things. All right. Now for the horizontal asymptote. This has 3 different rules. Yes, you need to memorize the rules, but we also have Desmos to help us remember these rules. So, if the numerator degree, remember that degree is the highest exponent. Okay. If the numerator degree is less than the denominator degree, so there's a bigger degree on the bottom, the asymptote is automatically y equals 0. If they have the same degree, it's going to be y equals the leading coefficient over the leading coefficient of the denominator. We're going to divide those, and that will give us our horizontal asymptote. If the numerator degree is larger than the denominator degree, there's no horizontal asymptote. And basically, we're not going to deal with that situation at all this year. You'll learn it more in pre-calculus. So basically, if the degree is bigger on the bottom, it's y equals 0, and if they're the same, divide the leading coefficients. So let's look at these. So we have h of x equals 6 over x minus 3 times x plus 4. So the nice thing is, they already factored the denominator for us. What's going to make these 0? Well, the first one would be 3. The second one would be negative 4. So those are our vertical asymptotes. So can't touch 3, can't touch negative 4. Okay? For the domain for this, based on these asymptotes, you can either write it as x such that x can equal 3 and negative 4. If you're going to write it in interval notation, I'm going to warn you, it's a lot longer this time because we have multiple asymptotes, and you have to pay attention to the order that you write it in. So it's going to go from negative infinity to negative 4, negative 4 to 3, and 3 to infinity. Because we need to make sure we're writing them from least to greatest. Now, should you be writing them from least to greatest in set notation? Absolutely. Does it still make sense if you don't? Yes. If you write set notation in the wrong order, it's not going to make sense because you can't go from negative infinity to 3 and then 3 back to negative 4. All right, our horizontal asymptote. The degree on the top would be 0 because there's no x's. The degree on the bottom would be 2 because if we multiplied this out, we'd have x squared. So since the degree is bigger on the bottom, our horizontal asymptote is y equals 0. Okay. For a range y such that y cannot equal 0. Because I'm running out of space, I'm just going to write that one. So we have this. Alright, so now I'm going to use that. I'm going to put it in Desmos to get the graph. So y equals 6 over x minus 3 times x plus 4. Okay, it looks like that. Now you can kind of see at -4 starts to go off this way and then it comes back this way. It doesn't look like it ever actually touches -4. That's because we have an asymptote there. Okay. Same sort of thing happens at 3. So that's helping us know not to graph there either. So we're going to have a lot of, this one's not that bad. 0, -0.5, but a lot of like the points on this are going to be weird decimals. We're not going to get any like nice whole numbers. So we're just going to give a general sketch. It looks like that. It looks like this. And then there's this like weird flatter piece in the middle. Okay. So end behavior. Remember, we're just looking at the ends. The right-hand side's getting close to the horizontal asymptote. The left-hand side's getting close to the horizontal asymptote. So both parts of our end behavior are going towards 0. Alright, so here's one. We don't need to factor the bottom again, and the only thing that's going to make just an x0 would be if x equals 0. And here, we have the same degree on top to the bottom. It's x to the first over x to the first. We want to look at the leading coefficients. That's our numbers in front, so 1 and 1. So 1 over 1 equals 1. So our horizontal asymptote is at y equals. So domain x such that x cannot equal 0. Range y such that y can't equal 1. And end behavior, we know it's going to go towards the horizontal asymptote, so towards 1. So to sketch our graph, I'm going to put it in Desmos. So 1, 0 is a point, and it looks like -1, 2. 0, -1, 2, and sort of sketch it in. Again, you can check your asymptotes. We follow along this line. The y's are getting bigger, they're getting closer to 1, but not touching it, and you can see the 0 there. Alright, one last situation that could happen. So, when we factor our denominator here, we get x minus 2 times x plus 2. If we look at our numerator, that also has an x plus 2. So technically those would cancel out, and they're going to cause a hole in our graph. Like literally it looks like somebody took a hole puncher and just punched one little hole in the graph. And I'll show you how it comes up on Desmos. The thing that would make these factors that canceled 0 would be -2. So that is the x value of the hole. What would be left here after it cancels is 1 over x minus 2. If I plug this -2 in, end up with 1 over -4, so -1/4. That is where the hole will occur. Our vertical asymptote is going to come from the factor that didn't get canceled out, so x equals 0. And then because our degree is larger on the bottom, our horizontal asymptote will be at y equals 0. We're not worried about the x-intercept or the y-intercept. You can get that off the Desmos graph if you want. So, put in y equals x plus 2 over x squared minus 4. So we said the hole was at -2. Like right now, that looks fine. There's no hole there. I mean, if I zoom in, there's no hole there. Let's look. What happens as I scroll across at -2? Oh, it's really, yeah. So there you go. It shows you that there's a hole there, and it says that the y value is undefined. And that's because it was originally in the denominator. So it's not going to give you the y value. You're going to have to calculate this on your own, but at least it'll confirm that there was a hole there. So if you're graphing this for class, so x equals 2, y equals 0. When you graph it, you go to -2, -1/4, which is like a quarter of the way down. I know that's not easy to draw on this graph paper in general, especially while we're doing things digitally. Just do the best you can. So we know it'll come over to this. And then we saw on the graph it kind of curves like that. Are there any good points on the other side? Let me zoom back out. That point looks nice. 3, 1. Perfect. 1, 2, 3, 1. It's a real dot. Let me make sure I close it in. Okay. So domain just be x such that x cannot equal plus or minus 2. We're still going to put -2 because there's a hole there. It can't equal that either. And then the range would be y such that y. That's all for today. See you in class.